Hi everyone, welcome back to the Coding and Analysis YouTube channel. And in today's video, we're going to run the XGBoost Regressor Model to determine the sales price using for the single family homes. And from the NVIDIA website, XGBoost is an open source software library that implements optimized distributed gradient boosting and machine learning algorithms under the gradient boosting framework. XGBoost, which stands for Extreme Gradient Boosting, is a scalable distributed gradient boosted decision tree machine learning library, provides parallel pre-boosting, and is the leading machine learning library for regression, classification, and ranking problems. So that's why we're using this in this model run that we're doing for the sold prices for single family homes in the city of Destin, Florida. So we start off with our features, updated feature columns. So what we're going to use is beds, baths, square feet, lot size, year built, waterfront, private pool, HOA, monthly fee, latitude, longitude, and a zip or postal code. And as we saw in the previous video, waterfront and private pool, we had to bring that information in using an XLOOKUP. I downloaded the original 173 homes here, and then in the data, I had to download another data set for the waterfront and another data set for the private pool. And I listed them as yes, there was waterfront, yes, it was private pool, and we got that information from the Redfin filter. And we just did an XLOOKUP to bring in the information. And so 1 is yes, 0 is no. There is no waterfront or private pool for the home if there's a 0. So we have the features right here, and then our function, we got our function right here, train and predict. And the parameters are property type and features. So these are the features up here. And we're filtering our data for the current property type right here. So we're just saying everything that's single family, we want it filtered. And since I took out the condo and the townhome, that's when that would have been this would have been needed, because if there was just had a big list of property types that were mixed in, this would have filtered and sorted everything. But since we're just doing single family homes, we're just saying property type is going to equal the right here, single family residential. So we have right here, if the data is empty, which I made sure there's no empty data, it would return print this out, no data found for property type. And then we're preparing the features and targets. The X, capital X, is the feature columns, and the Y is the target variable, and that's the sold price or price as it is listed in the data set. And then missing values to fill with 0 to avoid training issues, which I'm pretty sure I filled everything. There's nothing that's going to be NA or NaN. And then right here, we're resetting the data frame indices to align rows to filtering so all the information matches. So if we would have done a filter, if we had multiple property types, this would have reset everything to where all the information stayed with the rows and the data, and it wouldn't have moved and caused any problems. So we're just setting the indices to preserve the alignment of the data. Then we're splitting the data. So it's going to randomly split the data into 80 train, 20% testing, and then the IDX underscore train or index underscore train index underscore test. We use that to retain the information in the row indices to label the rows later. And then so you can see here, train, test, so we're marking the data split. So we have the training data, and we have the testing data. And then we have the train XGBoost model. So we're using the XGBoost Regressor model that we imported from the XGBoost library. And we have here number of estimators is 150. Max depth is 3. Learning rate is 0.1. And subsample 0.8. Column sample underscore binode 0.8. Regular alpha 0.1. Regular lambda is 1. So number of estimators is the number of trees that we're using for the model to learn on. And the max depth limits the maximum depth of each tree to 3, controlling model complexity, prevent overfitting by restricting how deep the trees can grow. And then the learning rate, also known as ETA, this scales the contribution of each tree. A value of 0.1 means each tree's contribution is shrunk by 10%, encouraging gradual learning to improve generalization. And then the subsample uses 80% of the data to grow each tree, introducing randomness to reduce overfitting by training on a subset of rows. And then the column sample by binode is 80% of features at each node split, adding randomness to feature selection to reduce overfitting and improve robustness. And then the L1 regularization is it's called, it's really lasso. It's a lasso term on weights. A small value of 0.1 to encourage sparsity and feature usage, helping to prevent overfitting. So really, like the feature importance is down at the bottom. If they're around 0, the model just gonna not include those. And then the L2 regularization or ridge is term on weights. A value of 1 adds a penalty to large weights, further helping to prevent overfitting. So if we have a feature importance that's like 50% or more, it's going to add, I guess, a penalty to try to prevent overfitting from happening, and we'll have a randomness to the model and not just a memorization that the model is taking on the training data. And then the 42 sets a seed for reproducibility, ensuring the same random splits and results are used each time the code is run. So we have to make sure we do that, because if we didn't have that, we didn't have the same results, we'd just get the different figures every time, and that wouldn't work. And then we're fitting the model right here, the XGB.fit method. So we're just we're getting the training data for the feature importance and the target variable train. So feature importance right here, target variable right here, and then we predict on the train and test right here. XGB.predict method, XGB.predict for the train and the test. So we're making our predictions and we're evaluating. And it's going to predict prices for the train and test sets. And then here we're printing the mean absolute error. That's what's going to show up with the, so this is our model, y-pred train, y-pred test, and the y_train, y_test is the actual results from the y target variable. So you just have to think of it as the actual sold price and the train split, the actual sold price and test split, and then the models train prices and the models train prices on the test split. Then we're getting our feature importance right here. So the most important is going to be at the top, least important is going to be at the bottom, and we're adding the L1 and the L2, or the regularization alpha and the regularization lambda, to penalize anything that's has a large weight and it's a small value. It could possibly remove that feature. So we'll see if it removes any after we run the model. And then this right here is, since we have more than 2 listings, we will all the single family homes are going to show up. If there was like a vacant home, vacant land, there's only one vacant land or something like that, it wouldn't include in the model. And then we run the model for each property type right here. And then we combine. So when we run the model, so it's the empty dictionary, then we're doing a for loop, and then we're appending the results into this empty dictionary list. And then we combine and round the predictions right here. So all the data is going into this dictionary, and then we're concatenating. And then we're exporting to the CSV. So this is what's the file we're going to use. And then we're in this data frame that we're exporting out the address, data split, property type, prediction, and price, or is what's going to be shown. So data split, training, test, property type, single family residence, our models, predictions, and the actual sold predictions. When we run the model, we get the MAE. So the training MAE is always going to be better than the testing MAE. And we can see here for the single family, the waterfront was most important at 28%, square foot at 24, and baths at 16.5, private pool at 8.1, HOA monthly at 6.6%, and beds in your builder at the bottom, and zip and postal code are at 0, so the that's not being factored in. So we run this model, we get the results, we get our MAE. So when we think of it, oh, that looks bigger, a lot bigger, but we're dealing with $1 million properties, or more, even more than that. Or I think the highest one was 6 million. So around 300, 500,000, then we get up all the way to the millions. So that's why this 390 isn't too concerning. So in the next video, we'll run the R-square score and the MAE to see how those results showed up. So thanks for watching, and see y'all in the next video. Bye now.